Hi everybody. So today we are going to review everything you need to know about circuits in 10 minutes. So you've taken a 3-credit class, you passed the exams, you worked all sorts of homework problems. Today it just comes down to two things: Ohm's law, Kirchhoff's voltage law, and a few details around the edges. So Ohm's law, V equals IR, everybody knows that. In this case we're going to use E as our voltage, I is current measured in amps, resistance is R measured in ohms. That's a really easy one. The symbol for a resistor is that squiggly line. We can put signs on it that the plus terminal of a resistor is the terminal the current is going into. And then we go into Kirchhoff's voltage law, which is fairly simple. It's sort of the electrical engineering metaphor for Newton's second law. And what it says is the summation of voltage around a closed loop of a circuit has to equal 0. And we'll show how this applies in a very simple experiment with a constant voltage source and a resistance and a current, and that creates a current flowing through our loop. So what is that current? Well, we apply Kirchhoff's voltage law and say En minus the voltage drop caused by the resistor is equal to 0, and that voltage drop by Ohm's law is IR. So we have this very simple equation. We can solve for I. It's En over R. And that's it in a nutshell. A lot of the circuits we're going to be analyzing are going to be just that simple. Let's put real numbers to that. Let's say it's a 5-volt source and it's a mega ohm resistor. The current is 5 over 10 to the 6 ohms. And the answer, of course, is 5 times 10 to the minus 6 amps, or 5 microamps. That's simple. Now keep in mind, though, that a resistor turns that electrical energy into thermal energy. And this is something we might not have talked a lot about in circuits class. And the rate at which that transfer happens is I times E, current times voltage. In that previous case, the current was 5 microamps, the voltage was 5 amps. That means the power, the rate at which it was converting electrical energy to thermal energy, is 25 microwatts. Pretty small. Resistors have a rating of how much, at the rate at which they can handle that, and it's usually something like an 1/8 of a watt or 1/4 watt. So 125 milliwatts, 250 milliwatts, so much higher than we're talking about. And you can also say the power is I squared R or V squared over R. Okay. Let's talk a little bit about circuit diagrams. We're going to spend a lot of time talking about that in this class, but what you see on the left here is probably how you represented these in circuits class. For a lot of these applications, it'll be much simpler. The loop will be implied. We'll just have the voltages near the top, the ground at the bottom, represented by that triangular array of lines. It's just a shorthand, in case you get confused by that. Okay, other components in addition to resistors. You've seen these before. We have capacitors. We have inductors, and the inductor symbol looks like a coil of wires, and that's almost always what an inductor is a coil of some kind. We have a class of resistors called potentiometers, which have 3 terminals on them. And I think what they do looks a lot like that. And then there's diodes. Capacitors are a dynamic element. In other words, you describe them with a differential equation. The voltage is proportional to the integral of the current, or the current is proportional to the derivative of the voltage. Inductors, the voltage is proportional to the derivative of the current. Both of these are transient. Okay, so for DC, when all the transients settled out, capacitors look like an open circuit, like they're not there. Inductors look like a closed circuit, which is just like a wire. Potentiometers can be used either as a variable resistor or as a variable voltage source. In one of your labs, you're going to use it as a variable voltage source. And then the diode. We're going to see a lot of these, often as just LEDs, light emitting diodes, but they're worth spending a little more time with. So we'll do that now. So one way to look at an electrical element is to look at the current voltage characteristic, which means the curve that relates the current and the voltage. To get a handle on that, let's imagine a resistor, right? What does the current voltage characteristic of a resistor look like? Well, we can plot current on the y-axis, voltage on the x-axis, and the resistor is a straight line whose slope is 1 over r. Pretty simple, nice linear element. Diodes are not linear, and they're pretty complicated, and their typical characteristic curve looks like this. There's a curve in the first quadrant, a curve in the third quadrant, and the thing to remember is that they're very different scales in those two. If we were to draw on the same scale, we can really get good detail out of it. So for example, in the upper right-hand quadrant, voltage is in tenths of volts, right? And often that curve, that little knee, is around 0.7 volts for a silicon diode, and the current is in hundreds of milliamps. On the lower left-hand quadrant, the scale of voltages is in hundreds of volts in the negative scale, and the current is much, much smaller, so it's like 10 microamps, right? So it's very nonlinear, and sometimes you need that level of detail, but for almost everything we're going to be doing, we're going to simplify this a great deal. We're going to say the characteristics looks like this, like the green line here, that at the forward bias voltage, anything above that, it just allows whatever current you can get. Anything below that, it allows no current to go through. And keep in mind, the voltage by this model, that forward biased voltage, won't ever get bigger than that. Okay, and we're going to talk about that in a second. But by and large, if the diode is forward biased, then it passes whatever current the circuit will deliver. If it's reverse biased, it passes no current. Okay, but notice that there's nothing to the right on our characteristic of the forward bias voltage, and that's an important thing to realize. And it can lead to what is kind of a contradiction if you're not careful. And I think, but it helps us understand how these things work. Okay, the current limit. So I said it'll pass as much current as delivered up to a limit, and that's related to the power dissipation of the diode. Just like a resistor, that power is equal to the current times, in this case, the forward bias voltage. If it gets above, whatever many milliwatts, the diode will fail. And usually it fails as an open circuit. Okay, so a silicon diode, let's look at this as an example. Let's say a silicon diode which has a forward bias voltage of about 0.7 of a volt. And we put that in series with a resistor. We say, okay, what's the current that's going to happen when we do that? So KVL says the En minus E of the forward bias minus E of the resistor equals 0. And you put in what we know, and we solve for I. And I is equal to En minus 0.7, that difference divided by the resistor. So pretty straightforward. So here's a common application of this. Let's say we have a light emitting diode. So that's not silicon, it's germanium and often other chemicals. And its forward bias voltage is probably closer to 2.3 volts or so. And we're supplying with a 5-volt power supply. So what do we do to make sure the LED stays within its current limit? So it's got a current limit of 10 milliamps, forward bias of 2.3 volts, and a 5-volt power supply. So what R in series is going to be required to make sure that I stays below 10 milliamps? This is like Mechatronics 101, right? So here's our circuit, and here's Kirchhoff's voltage law, right? 5 minus 2.3 minus IR equals 0. IR equals 2.7, right? R is equal to 2.7 over I. I is 10 milliamp. Yada yada yada. Very quick. 270 ohms. Okay. And that's actually, and when you're using an LED with a 5-volt output of a computer, almost always it's a 220, 330 ohm resistor to limit that. Okay, here's a thought experiment. We're going to go through this very quickly. What happens if we don't put the resistor in there, right? Well, I said the voltage really can't get above the forward bias. Well, it can if you look at the real curve, but that intersection of the real curve at 5 volts is at a huge current, according to that formula, which is way above the current limit. And so what happens is the current limit is exceeded, and if you hook this up, and you can try it if you want to do it, but you'll get a very bright LED for a tiny, tiny period of time, and it goes dark, just like that. So that's it. That's my summary of electric circuits in 10 minutes. So thanks very much.